Okay, in this video we're going to look at biasing multiple transistors using a single voltage reference. Now we can do this with MOS transistors or with BJTs, but BJTs have a special property that we're going to examine in this video. So we can start by writing KCL at the supernode here. So we have the reference current being generated and flowing into the collector of Q0, but we also have some base current that flows. So we can write KCL is equal to, or IR is equal to ICO plus IBO plus IB1 plus IB2 all the way out to that nth transistor IBN. Now we know that the collector currents should be more or less equal, so we should be able to say that ICO is equal to, or approximately equal to, IC1. Now, of course, this is only explicitly true if the transistors have infinite output impedance or if the collector to emitter voltages are equal to one another. But if the collector to emitter voltages aren't equal and the output resistance is high enough, then this approximation is true. Now, we're going to further say that ICO is equal to IC1 is just equal to an output current. We're going to say is equal to IO. So now we can make a substitution. If we assume that all the devices have equal area, then we can write that IR is equal to IO plus IO times N divided by beta. This last term here is accounting for all the base currents. All right, so rearranging this, we can say that IO is equal to IR divided by 1 plus N divided by beta. Now, we call this term in the denominator a systematic error. Now, this systematic error is happening because the transistors have finite beta. In other words, there is always some base current flowing into devices. If beta is very large, then the error is very small. But if beta isn't very large, then the error grows. And you can also see that the more transistors that you connect to the reference generator results in bigger error. Now, it doesn't happen with MOS transistors, and this is because MOS devices have infinite resistance at DC at the gate. This means that we don't have any DC gate current flowing into the MOS device, so we'll never see that systematic error. Now, we can also ask, can the error be reduced? The answer is yes. We're going to buffer the base current, and we're going to do this using an emitter follower in a formation that we call the beta helper. And we'll look at that in the next video.